Welcome to the introduction to the equilibrium constant and the concept of equilibrium. All right, so a lot of times when we think about chemical reactions, we tend to think about them as being unidirectional. We usually only think about the forward reaction, but the truth of the matter is that most reactions occur in both directions, and we say that they are then reversible. Now, usually one reaction will proceed is more favorable than the other. So, generally speaking, maybe the forward direction is far more favorable than the reverse. So you may end up with more products than reactants as a whole, but both the forward and the reverse reactions can happen at the same time. So equilibrium is a special state, and we call it a steady state, where the rate of the forward and the reverse reactions are equal. So again, in a reversible reaction, right, you can have the rates changing. Equilibrium, again, is a steady state where those rates become equal. And at this steady state, the concentrations of the reactants and the products will remain constant. So in equilibrium, it looks like nothing is changing. It looks like the reactants and the products are kind of staying stationary. And the reason for that is because these processes are happening at the same speed. So reactants are being converted into products at the same rate that products are being converted back into reactants. So again, there's really no flux in the concentrations. Okay. The most tangible kind of representation of equilibrium would be homeostasis. So homeostasis is another kind of steady state where, our temperature, for example, will remain 98.6. However, there are processes happening. We heat up, we cool down, we, burn energy, cellular respiration. We can also sweat to release heat. So, that's kind of a human system or a living system equilibrium. But reactions have equilibrium as well. All right. So these plots are for a reaction that you initially start with all reactants. So, okay, let's look at these. The top plot is rate versus time. So this is a classic kinetics plot here. And then we have the amount or concentration versus time on the bottom. So another classic kinetics plot. All right, let's look at the bottom first. So as you can tell, and as I said before, at the beginning of this reaction at time 0, you're starting with 100% reactants, 0% products. As this reaction proceeds, right, the reactants are going to be consumed and the products are going to be formed. Okay, we also looked at the fact that this is an exponential process. We saw that when we were studying kinetics. Now, if you look here, this steady state, where these lines level off, where the reactant and product concentrations become constant. Operative word here is constant, not equal. Constant. They don't change. That's equilibrium. And as you can see from the top plot here, that's when the rate of the forward and the reverse reaction become equal. So again, the forward reaction started off happening at a much faster rate because you started with all reactants and no products. However, as your forward reaction continues to proceed, you begin to create more products, right? And the more products you create, the higher the concentration of the products that you have, which then allows for a higher probability for that reverse reaction to proceed. And that's how you reach this steady state of equilibrium. Okay, so how do we describe equilibrium? Equilibrium is actually equal to a number, and that number is called K. And very, very important, this is capital K, not lowercase k. This is not the rate constant. This is the equilibrium constant. State function, capital K. This is a number that expresses the relationship between the amounts of products and reactants that are present at equilibrium. And very importantly, K is dependent on temperature. So for one reaction, K will vary with every temperature. All right, so how do we calculate the equilibrium constant? Okay, so the equilibrium constant K can be represented a number of ways. It can be calculated kind of as a unitless number by concentration or pressure. Very importantly, solids and liquids are left out of the equilibrium expression. So if you see any reactant or product that is solid or liquid phase, it does not appear in the equilibrium expression. You can leave it out. This includes water. Very important. All right, so let's use an example reaction here where A plus B goes to C plus D, where the capital letters represent the molecular formulas and the lowercase letters represent the stoichiometric coefficients in the balanced equation. Generally speaking, you have the equilibrium expression equals to products over reactants. And the way that we would represent this is the concentrations of the products are multiplied together in the numerator, and the product of the reactants is taken for the denominator. Also, very importantly, each concentration is raised to the power of the molar coefficient in the balanced equation. So again, to just break down that symbology, the product concentrations are numerator, reactant concentrations are denominator. Each of those is raised to the molar coefficient of that substance. The brackets indicate molarity, just as review. K subscript C equals the concentration equilibrium constant. K subscript P is for partial pressure equilibrium constant. And K, again, K or KEQ is just unitless. Very important, which will be revisited later. Kc and Kp are not interchangeable. They are related through the ideal gas law. However, they are not completely interchangeable. They are not equal to each other. Alrighty, so let's go ahead and look at an example here where we have NO, 2NO plus O2 going to 2NO2. All right, so if I want to write my equilibrium expression, again, K is equal to products over reactants. Okay, so what I'm going to do here, K equals my product. I only have one product, which is NO2. So I'm going to put that in brackets, and I'm going to raise it to its molar coefficient of 2. All right, and all of that goes over the reactants. So I have two reactants. I have NO and I have O2, where NO is raised to the second power because the molar coefficient in the equation is 2. So this would be how to express the equilibrium constant for this reaction. Okay. All right. Sorry, I cut the image off here, but what is the point of K? What does K mean? K will indicate which reaction is favored, the forward or the reverse. So if K is greater than 1, that means that your numerator is going to be much, much larger than your denominator. If K is much, much larger than 1, that means that your products are going to be favored. The forward reaction is favored. Okay? So if you look down here at this image, and I apologize it's cut off, but you get the idea. When you have a large K, you're going to have way more products at equilibrium than you will have reactants. All right? Now again, at equilibrium, the rate of transfer will be equal. However, at that equilibrium state, you will have more products than reactants. All right? Now vice versa, if K is less than 1, that means that your denominator has to be much larger than your numerator. So you would have way more reactants than products. And as you can see in this image here, that's what we're showing you. And a small k would be anything with an exponent smaller than -3, we would say. Then you would have way more reactants than products at equilibrium. And what we're showing here, there's kind of an intermediate range. So anywhere from the order of -3 to 3 for your equilibrium constant. We generally say that those reactions have approximately equal forward and reverse rates. All right, which isn't terribly common, but it certainly does happen. Alrighty. So, what happens when to the equilibrium constant when the reaction changes? So how do we manipulate the equilibrium constant for a changing reaction? And we're going to go through these kind of one by one. All right. So Okay, first, if you have a reaction and you're taking the reverse of that reaction direction, what you're going to do is actually take the reciprocal of K. So K of the reverse reaction is equal to 1 over K of the forward reaction. So again, you just take the reciprocal if you're changing the direction of a reaction. And that's what we're seeing here in this slide. So what they're labeling is Kc is going to be for the forward reaction, and Kc prime, with this little apostrophe, that's a prime in science, that's going to be for the reverse. And what we've done here is, we're writing the equilibrium expression. We have products over reactants raised to their molar coefficients, right? So if in the forward reaction, C and D are the products, A and B are the reactants, so this would be your Kc here. And as you can see, for the reverse reaction, everything is just going to be switched, right? The products become reactants, reactants become the products. So yeah, your equilibrium constant is just going to be the reciprocal of what you did. All right, now, if you have a mechanism, if you have a multi-step reaction, and you're trying to determine K for this reaction, it is taken as the product of the equilibrium constants for those individual steps. So if you have a reaction that is, made of 3 elementary steps, for example, then the overall rate constant would be equal to K of the first step times K of the second step times K of the third step. All right, and that's what we're kind of seeing here in this example. So in the first reaction, you may have an intermediate being formed, but when you look at the overall equation, right, the overall equation has the net reactants and the net products. So the intermediates, whatever intermediates are formed in those elementary steps, as you can see here, if they're products in one step and reactants in another step, then they will be in the numerator and denominator of those multiplied coefficients, so they would cancel out. All right, so again, when you have multiple steps, you would just multiply those K's together, and that will give you the overall rate constant. Okay. And finally, what happens if you multiply the entire reaction by some stoichiometric coefficient? You would then raise the K constant to that molar coefficient. So, for example, if you look at this reaction here, the top reaction shows N2O4 going to 2NO2. The second reaction is that first equation multiplied by a stoichiometric coefficient of 2. So 2N2O4 goes to 4NO2, right? So this is just the same thing multiplied by 2. And as you can see here, when you're writing the equilibrium constant, again, just writing it, products over reactants, raising the molecules to their molar coefficients, when you multiply all of your coefficients by some number, it changes the exponent of that reaction by whatever that number was. So by simply raising K to that molar coefficient, you can kind of sidestep all of this. All right. And very importantly, last thing, again, as I said in the beginning, Kc and Kp are not interchangeable. You need to actually calculate the conversion here, and this is the equation that we use. K sub P is equal to K sub C times RT raised to the delta N power. All right, and delta N is going to be the change in number of moles of gas from reactants to products. So the way that you calculate it is, the product gas minus the reactant gas. And we're talking about the moles. So these again come from the molar coefficients in the equation. R is your universal gas constant. You're going to be using the pressure mole volume constant here, because that's basically relating pressure to concentration, right? When you see mole and liter in the same expression. So you're going to be using this R, and then your temperature always has to be in Kelvin. So degrees Celsius plus 273. The only time that Kc is equal to Kp is if the number of moles of gas in the reaction doesn't change. And we'll actually see that when we look at Le Chatelier's principle in the following lessons. So that is a very quick introduction to the equilibrium constant. We are going to be looking at in the future how we can reach equilibrium by looking at the value of this constant as a reaction quotient tomorrow. So if you have any questions, feel free to drop one in the comments, or you can always email me, and I'll see you next time.